In this webinar, we will discuss the basics of accurate battery fuel gauging, the benefit it provides to the end user, and which competing approaches are available and how these stack up against each other. Towards the end, we'll show a practical example of how to set up accurate and energy-efficient fuel gauging on an SoC running Zephyr. Welcome to this Nordic Tech webinar. This webinar is called Easy Fuel Gauging for any battery-powered Zephyr RTOS application. My name is Robin M. Saltness. I'm a Senior Product Marketing Engineer here at Nordic Semiconductor, and I'll be your host and speaker today. Let's get into the topic of today's webinar. What is fuel gauging? Fuel gauging gets its name from the automotive industry, where fuel is liquid and measured with a flotation device and displayed through some sort of dial indicator like we see on this picture here. That is not what we will discuss in this webinar. Fuel gauging in embedded devices refers to the battery's state of charge, most commonly given in a percentage of fully charged and referred to in daily speech as battery percentage. We normally know it as this symbol that is used to indicate the state of charge, often also accompanied by some sort of percentage value. And the fuel gauging is the process that is used to determine what this icon should display, and the accuracy of your fuel gauge decides what granularity you can offer on the different levels of charge. So what benefits do this provide to the end user of an application? Well, first of all, it's a customer expectation, really. Everyone who uses low power embedded devices expect to know at least for some amount of certainty that their device is not about to die and at any moment's notice. And if you have accurate fuel gauging, this requires the customer to charge less frequently because he doesn't need to charge just in case the battery is low. He can know for sure that the battery isn't low. And this provides the customer with a longer perceived battery life. So even if your battery life is exactly the same as before, the customer will think that, oh, I still have this much left, I don't have to charge. That gives them a positive impression of the battery life of the device, which in turn could lead to making the same solution with a slightly smaller battery, because it's even if the actual battery life is shorter, the customer will have the confidence to go lower on the charges between charging the device, and it allows you to build a more compact system. So, which approaches to fuel gauging does exist in the market? Well, there are basically two main contenders here. It's the open circuit voltage lookup, which is a lookup table of the different voltages a battery can have, and then just one-to-one relating this to a battery percentage. The other option is using dedicated fuel gauging hardware. And there are also multiple types of devices here, and we will talk about them a little bit later. But maybe there's a third way. Maybe there is a better way. But let's talk about the OCV method first, the open circuit voltage. And this is a problem especially with lithium-ion batteries or lithium polymer batteries. And that is discharge curves. So in an ideal world, discharge curve would be a linear line from your max voltage and down to your minimum voltage. And then a voltage lookup table would be perfect. It would be very easy to relate voltage to state of charge in percent. Unfortunately, in the real world, voltage discharge curves don't look like this. They look more like this. They have a really flat section in the middle, and as we see, the difference in the voltage between 80% and 20% state of charge is really, really small, which makes it necessary for lookup tables to be very, very precise. Unfortunately, this curve changes with temperature. So if the lookup table was made to be very, very precise, measuring very slight differences in voltages, they get thrown off by miles when there is any sort of temperature swing. And this makes this technique inherently unreliable. Then we have the dedicated fuel gauging hardware Here it's personified with a coulomb counter, which I have named the most expensive way to drain your battery, but there are also other options. Two main options are the coulomb counting gauges and the discrete hardware fuel gauges. Coulomb counting gauges has the best accuracy. It counts every single charge leaving the battery. So in the beginning, this will give you a perfect state of charge. Discrete fuel gauges also have good accuracy. They also work in the sort of the same way as the third option that we will discuss a little bit later. Both of them, though, adds extra cost to your bill of materials, and they both also take up extra space on your PCB in the sense of an additional component. Both of them also consumes extra power. The coulomb counter is especially bad because it consumes power even at system off, and because it needs to constantly track all the charges leaving the battery, even the ones who are leaving it when the system is off. And to make matters worse, their accuracy is sensitive to accumulation errors, meaning that errors that are happens in this coulomb counting process will add on and pile on to each other, and it will be less and less accurate as time goes by. The discrete fuel gauge, hardware fuel gauges, works in a slightly different way. It takes in some voltage, current, and temperature information from the battery, and then it uses an internal processing core to calculate the state of charge based on this. And tuning this algorithm, that it needs to be tuned to the battery you're using, and this is a service that is usually sold as send in your battery to us and we will do it for you by the fuel gauge supplier. So in a full system and power management application, you will have a power management subsystem that looks a little bit like this. You have a dedicated charger IC that charges the battery. Then you have power regulation that makes sure that the sensitive components get the right voltages. And then you have the fuel gauge chip. Let's say this is a hardware fuel gauge algorithm based for now. And so it happens that you can get all of these with just one component if you use the NPM 1300 PMIC. We thought that this all could fit in one package, and we have made them into one component. There's a small asterisk here, and that is that the NPM 1300 PMIC does not contain a system processor that you need for this fuel gauging, this algorithm-based fuel gauging to work, but it has the other hardware. So how do you solve this? Well, let's say you implement a system with a dedicated fuel gauge chip. You still have a main system processor, because that is typically the purpose of your whole device, is to do some processing, either if it's a Bluetooth SoC or if it's MCU that does something that isn't communicating wirelessly. You have some sort of processing task going on. It could be a small processing task, it could be very easy, or it could be more complex. But you will always have this. And for the NPM 1300, we decided that it made sense to outsource the fuel gauging algorithm processing to whatever main system processor you're using. So instead of having this 4-chip solution, you have a 2-chip solution where the main system processor is used both for your main application and also does the fuel gauging processing on the side, and with the help of the hardware that is implemented in the NPM 1300 PMIC. And this gives you one big benefit. So the NPM 1300 fuel gauge adds around 3 microamp when pulled every second to your software application. So here's an example from an anonymous Nordic customer. They have a 46 milliamp hour battery, and their application draws less than 200 microamps of average current draw. They looked into adding a discrete fuel gauge component, and that component's power current draw looks like this. In normal mode, system on, this component itself would draw or add about 25% more current consumption to their application. So for them, they simply can't allow the application to have this type of fuel gauging, and the only way they could have it was by implementing it from the NPM 1300, where it adds a very minuscule amount of current draw to their final application. So I've been talking a little bit about the NPM 1300 now, and let's go through it a little bit more in detail what it does. So the NPM 1300 is a PMIC with ultra high efficiency buck regulator. It has these unique system management features and an accurate ultra low power fuel gauge. So when it comes to its electrical capabilities, it has two buck regulators that are individually adjustable between 1 and 3.3 volts. They can deliver up to 200 milliamps of current each, and they are over 92% efficient. We also have two load switches that are digital controlled over I2C after startup. They can switch up to 100 milliamp currents, or they can be driven and used as LDOs, where they can deliver up to 50 milliamps at between 1 and 3.3 volts. Then you have the battery charger that charges single cell lithium-ion, lithium polymer, or lithium iron phosphate batteries. The available charging currents are 32 to 800 milliamps, and the termination voltage can be selected in a range from 3.5 to 4.4 volts to accommodate a big variety of different batteries. This battery charging is supported by a USB-C compatible input or any 5-volt DC power supply, really. Then we have some system management features as well, like failed boot recovery. It's basically just a timer that looks for a I2C message after boot up, so that if it doesn't receive this I2C message, it can do a power reset of the entire system. Hard reset is a 10-second timer that allows you to pull one pin on the PMIC low and then for 10 seconds, and if you have it low all the time, it does a full power cycle of the device. This is also often implemented as a discrete component in the end devices. Hibernate is a version of our ultra low power ship mode, which is used for shipping, but here it's used for sleeping. So in addition to the 370 nanoamps that you get in the normal ship mode with the NPM 1300, we run a timer that uses 130 nanoamps extra, so for a total of 500 nanoampere. And it allows you to wake up at certain points and check if the application needs to be running or if it needs to be sleeping again, and then it can go back into hibernate. Watchdog timer is just an additional timer that lives in the PMIC that can be used for an extra layer of protection for your application. And then we have this really interesting power loss warning that detects sharp transients on the power inputs on the PMIC side. And if it detects battery and USB being disconnected at the same time, for example, then it can set a flag on a GPIO output on the PMIC and tell your system to do a controlled shutdown or save some settings before the decoupling capacitors of the system runs out of power and the device stops working. But let's get back on topic to fuel gauge. And the fuel gauge principle in the NPM 1300 is quite simple. It is like this. You have a battery that is connected to the NPM 1300. Then you have this NPM 1300 with its internal hardware that monitors current, voltage, and temperature. And then it sends this over I2C to your host SoC, which runs the fuel gauge algorithm. And to make life a little bit easier for the developer, we have decided to make ease of use better with implementing this intuitive GUI to configure, export, and implement this functionality. And it's fully supported by the NRF Connect SDK through the NRF Connect for VS Code application extensions as well. This will lead to a better quality of life for everyone. So the hardware designer doesn't need to write any code because it can just be configured by a GUI. And the software developer does not need to read data sheets that are normally required for setting register manually, because it also has this GUI that allows them to see all the available settings. And in this software is where you do the first battery characterization for your fuel gauging. So for the one time only, when you have decided which battery you want to use for your final application, you do a one-time battery characterization. So the NPM 1300 evaluation kit and the NPM fuel gauge board are connected together. You hook up your battery to that, and you run the NPM Power Up app's battery model generator. So it will do 3 full charge discharge cycles of your battery. It should be once on the minimum temperature you expect your device to be used at, one for the maximum temperature you expect your device to be used at, and one for the normal operation temperature of your device. This will generate a battery model that you then load into your firmware application for whatever SoC or MCU you're using. And once this is connected with the NPM 1300 during runtime, it will use the current voltage and temperature measurements from the NPM 1300 reported over I2C to give you a pretty accurate state of charge of the battery. And how accurate, might you ask? And we have taken this fuel gauging philosophy, and we have decided to compare it to the open voltage lookup table. Open circuit voltage lookup table. So you can see here there are 3 lines on the top graph. You have the state of charge prediction from a coulomb counter, which is 100% accurate at the start, as we said. And you can see that is the black line, and there's a blue line right below it that is the NPM 1300 fuel gauges predictions, which are very, very close. And then you have the gray line that is the OCV-based lookup table, and you can see it fluctuates a lot and it deviates a lot more. And on the bottom graph, you can see the instantaneous estimation error when the coulomb counter is used as a reference. You can see that the error for the OCV is up to 20%, but it's hovering normally around 10-15%, whereas the NPM 1300 does never stray above 3%. And this was actually done under a pretty stable temperature, which would indicate that the NPM 1300 is good under normal conditions, and the OCV method is not even close under those conditions. But most devices don't live their whole life between 23 and 25 degrees Celsius. Sometimes they're taken out. So we redid the same test when we subjected the battery and the system for a big temperature swing from 40 degrees down to minus 10 degrees and back up again. And you can see that the OCV-based lookup table is really getting thrown off by this. It reports over 30% wrong compared to the coulomb counter, whereas the NPM 1300 stays below 5% even at these extreme conditions. So if we do the same test, so which SoCs are compatible with the NPM 1300 PMIC? Well, all and any MCU that you can find with I2C is supported with the system management features and all the power regulation features. So battery charging, buck regulation, and the different recovery features are all supported on any I2C enabled master device. For the NRF 52, 53, 54, and 91 series devices, this is achieved through the NRF Connect SDK normally. If you have a NRF 52 series working on the NRF 5 SDK, this is also possible to use, but it's not recommended. For any Zephyr-based microcontroller, you can use Zephyr. Here you will have the same support as in NRF Connect SDK. For MCUs on any other SDKs, you will be using the NPM-X library, which is a part of our MDK, which is used when you are using the non-Zephyr SDKs. On a bare metal MCU, you can always look up which data sheets, which registers that need to be set in the data sheet. So it's a manual process, but it is possible and it's usable. Fuel gauging is fully supported on all current Nordic SoCs and SiPs. On Zephyr, you get experimental support through Zephyr. It requires an ARM Cortex-M4 or M33 processor. The same with the NPM-X library devices. Fuel gauging is not supported if you're doing bare metal. Supported power sources all depends on the power requirement of your SoC, SiP, or other MCU, and we won't go deeply into that in this webinar. So for the demo of this, we need to make some connections between the PMIC and the SoC that we're using. So first of all, we need to power the SoC. We're using Buck2, Vout2, and it's connected to VDD input on the SoC, and you also need to connect VDD I/O on the PMIC, so they are on the same voltage level for the I2C communication. Then we need the two I2C communication lines, and everything. All of this is obviously on a common ground. And battery is connected to the battery input of the PMIC, and also if you're charging, USB power is connected to the VBus input of the PMIC. If you have any other devices that are consuming current, active devices, you will connect them to either the other buck, or if you have a device that needs more than 200 milliamp, you will have to connect it to the VSys output of the PMIC. This is an unregulated output, so it follows the voltage of the battery when running from battery, and it gives you the charging sources voltage, so typically 5 volts USB when you're on a charger. And this can deliver over 1 amps, so here there's plenty of current to be had for current consuming devices. This is important because if you're using fuel gauging, connecting this device directly to your battery, even though it will be compatible with it, means that it will not be counted towards the current consumption that is being used for fuel gauging. So it's important that this is drawing from the PMIC as well, even though if no current or voltage regulation is occurring. So here is the short walkthrough of what we will go through in the demo now. So first we will have the NPM 1300 evaluation kit and the NPM fuel gauge board. We will profile a battery using the NPM PowerUp software, and then we will export this battery profile from NPM PowerUp into our VS Code application. We will use the fuel gauge library and some pre-made samples to referencing this battery model file to have fuel gauging running on our ARM Cortex-M4 processor that we are using in the NRF52833 development kit that we are using for this. So to add fuel gauging to an application, we first need an application to add it to. For this, I will just copy a simple Blinky sample from the NRF Connect SDK version 2.7, which is what I'm at now. This is a very basic sample, so it will contain none of the things that are required to do fuel gauging to start with. As you can see, it shows up here under my application in the NRF Connect for VS Code extensions. Then we need to prepare a little bit for adding support for fuel gauging. So the first thing I will do is that I will go to NRF Connect for desktop. I will open NPM PowerUp, and I will set the settings of the PMIC that are going to be used, except for fuel gauging. So enable fuel gauging here, enable the charger. So I'm using a 3.7 volts nominal battery, which means it charges up to 4.2, and my battery is quite large. It's 1400 milliamp hours, so I can use the full charging speed of the PMIC. Buck2 is what will be powering our system, so I will set it to 3.3 volts digitally. Then I will also enable the LDOs so that we are drawing a little bit more current through the resistors on the EK when we are using the application. Then I will export this configuration and put it in my application folder named Blinky Webinar. Then we also need a battery model for our specific battery. So here I have prepared a NPM 1300 evaluation kit with the NPM fuel gauge board, the battery we're using, power to the PMIC to charge the battery, and then a USB connection to the computer to do the profiling and communicate with NPM PowerUp. So the NPM fuel gauge board is an add-on to the NPM 1300 evaluation kit that is basically just a battery current sync device that allows you to draw a set amount of current through the entire discharge cycle independent of what the voltage of the battery is. So in NPM PowerUp, we will then connect to the EK and we will profile the battery. So we click on profile battery, we name your battery, whatever, then you set the termination voltage, so 4.2 volts for this battery, discharge cutoff voltage, so our minimum voltage for the battery, here's 3 volts. Capacity of the battery, this should be the capacity that the manufacturer gives for your battery, so for me it's 1400 milliamp hours, and then the charging current, which I will use the full current of the PMIC. And the capacity here doesn't really matter because the fuel gauge board will estimate or measure the actual capacity of your battery. This just decides what discharge current you will run at. So select the capacity that your battery manufacturer has given on the battery specs. Then we select the thermistor. I have a battery with a 10 kilo ohm thermistor. If you have a battery without thermistors, you can ignore, or if you can have other thermistor sizes, you can select them here. Then we will profile the battery over different temperatures. So one normal temperature, 25 degrees Celsius, which I expect the device to be used at the most of the time. And then the minimum temperature I would expect the device to be used at, and also the maximum temperature that I expect the device to be used at. And this will give you a accurate fuel gauge estimate over a range of temperatures, over all temperatures. Then you just select the folder where you want to store it, and you save it there. I have a folder for batteries, my battery models, and I can just save it here. Once that is done, it will start this process, and it will go through the discharge charge cycle 3 times, and it will tell you to change the temperature in due time. And this will take about a weekend, so we can't sit here for all that. So I will just abort. And if the battery were allowed to, the profiling were allowed to complete, then we could go to profiles and we could find it here. So here is the uncompleted profile. But to continue on this webinar, we will need a profile to work with, and I will just take one of the bundled profiles with the app, and I will select a 1350 milliamp hour one, which is the most closely aligned with the battery we have, and I will save this model. So I will not save it in the folder with the battery models. Actually, I will put it in my application folder. So in my apps and my Blinky webinar, I will put it here in the source folder, and then I will give it a different name. I will give it the name battery_model, because this is the name that is expected from the application that we're going to copy parts from at a later point. Then we also need to add the build configuration to our application. So we will select the kit we're using. I'm using the NRF 53233, sorry, DK. And I also need to add the extra device tree overlay for the NPM 1300 PMIC that we generated in NPM PowerUp. And because I'm going to do some changes to this project, I will not build it after generating configuration. So the first thing we have to do is we need to tell the DK which I2C pins we want to use to communicate with the NPM 1300. So I will go into the config files and actually look at this overlay that we created in NPM PowerUp, and I will attach to it the settings for the I2C pins that I am using on the DK. So in this case, I'm using port 0, pin 26 and 27, and the code for selecting those would be this. So pin select 27 and 26. And they also need pull-ups because there are not pull-ups on any of the kits. So that is all you need to do to the overlay. Then we also need to pull in some kconfigs in Zephyr. So here we need to add the setup that are needed for basic PMIC functionality. So that will be these settings. These settings. Then we will also need to add the config for fuel gauging. Yes. And then we also need to add floating points operations because we are printing out the state of charge as floating points. And that is what we need to do to the kconfig file. And we still haven't done anything to our main C files or any of the files in the project related to the application's runtime operation. So first of all, we will cheat a little bit. So we will go into our NRF Connect SDK source folder, and we will look at a sample called fuel gauge. So here's my NRF Connect SDK folder 2.0, which is what we're on. And then I will go to samples. NRF samples. PMIC. And then I will select the fuel gauge sample and select fuel gauge.c and fuel gauge.h. And I will copy them over to my specific project. I will put them here in the source folder. When that is done, I can go back to VS Code and I can go into my manifest, so the CMake lists, and I will add the fuel gauge.c as a target source for my application. And if you look at the fuel gauge.c file, we can see that it expects our battery model to be called battery_model.include and be in the same folder. And that is why we named it that and saved it as that. So what this fuel gauge.c file does is that it prints out the fuel gauge values when function fuel gauge update is called. And that is what we will do next. We will go into our main.c and we will add this function call. So first we will add fuel gauge.h. Then we need to set up or we need to define our charger device, which is what we are calling the device that we are talking to when we are doing fuel gauging for this sample. So just a structure. Then we only need to initialize the fuel gauging, so fuel gauge initialize for charger. And then we also need to call fuel gauge update once every second. And that is what we're doing here. The sleep timer there is for 1000 milliseconds to blink the LED. And when we're calling this function, we will print out the values that are being used for or being the result of the fuel gauging process. So then we can build. And as it is building, I will prepare my NRF52833 development kit and connect it to the NPM 1300 evaluation kit. So it's ready. So what I'm doing is I'm connecting the output of the buck regulator to the input of the DK. And I'm also connecting the I2C lines, I2C lines, to the I2C on the PMIC. Then it completed its build, and then we will try to flash it to the device. And as we can see, it is now blinking. And if we connect to the terminal of the dev kit, we are printing out the state of charge of this battery. It's 96.96, and you can see that it's slowly decreasing because we are running the buck regulators through to resistors on the EK that are consuming current. And you can see that the current consumption is about 40 milliamps. That's all you need to do to add fuel gauging to an existing NRF Connect SDK application or any Zephyr application that are running on a compatible ARM Cortex M33 or M4 processor. And with that, I think we are ready for some questions. The first question is, can we discuss if this would be applicable to non-rechargeable lithium cyanol chloride batteries that have flat discharge curves. Yeah, we can discuss that. So lithium CoCl2 batteries have nominal voltages of around 3.6 volt, which is very similar to the lithium ion and lithium polymer and lithium ferrous phosphate that the NPM 1300 normally is used as a fuel gauge for. And that means that you could potentially create a fuel gauging profile that matches the discharge curve of your battery. The important part to remember if you want to use the NPM 1300 PMIC like that is that you must never enable charging, because we know what happens when you try to charge non-rechargeable batteries. And another important step is that you can't create this discharge curve using the tooling that we provide, the NPM power-up, because this requires to automate the charging process into it as well. So if you have a serious use case for this, I would recommend that you go to nordicsemi.com and click on the drop-down menu on the top of the page. And at the bottom of the drop-down menu, you can see a little button that says Planning a Project. And if you click that Planning a Project text, then you get a contact form that allows you to come in contact with a Nordic representative that you can discuss this with. So let's just show that question first. I forgot. Then we have another question. Does this only work with ARM Cortex M33 or M4 processor as a software limitation, or is the hardware limitation? It is a software limitation, and it is because we are providing this as a pre-compiled binary, this algorithm. Your profiles and what you make with the power-up, these are, of course, open, and you can look into them, but the algorithm itself is distributed as a binary to protect our IP. You know how this is. And porting to other cores is possible, but because we need to protect our IP, this has to be done by Nordic. And again, contact a representative through our web pages, and then you can discuss this as a business case. Then there's a question: what is the minimum current that can be effectively gauged by the NPM 1300? The minimum current is 0. This is because the NPM 1300 fuel gauges will normalize very quickly after the system is being fully powered off. So unlike a coulomb counter, for example, which stays on all the time and tracks every single charge that leaves the battery, the NPM 1300 uses parameters that it gets from the battery when the system is on. And even if the system has been off for a long time and some self-discharge has happened, the NPM 1300, after a while, a few seconds or a few update cycles of the fuel gauge algorithm, it will normalize to a value that is more or less correct, as if the system had been on the whole time. So 0. Let's see here. There's a very technical question. Does fuel gauge C contain the entire fuel gauge algorithm, or is there some binary-only library that implements the core algorithm? Yes, so the core algorithm is a part of, when I use it in NRF Connect SDK like this, it is a part of Zephyr. So it's actually pulled in by enabling the kconfig for it. Fuel gauge.c, as I copied in this example, is more about using that fuel gauge library to print out the value. So you could absolutely use fuel gauging without copying fuel gauge.c. This is just the easiest way of adding it to an existing application and get a printout immediately and see the results fast. You can use the fuel gauge library directly without copying any files as well. It's just a little bit more digging into the documentation that you have to do. Let's see here. You mentioned retrieving voltage, current, and temperature from the NPM 1300 via I2C once per second, resulting in 3 microamp. Is the NPM 1300 sampling current and voltage faster internally, and how fast? I'm not sure of the speed of this, to be honest. The once per second is something that you set in your application. So potentially as fast as your I2C bus can handle is the polling that you can do on these parameters, as far as I understand. So it's not limited to once per second, but once per second is what we used when we did our measurement of how much the current of your application running on the processor, how much current it adds to your application running on the processor. And this is what we think is a good value if you want to have very accurate fuel gauging. You can also run it less frequently and get a little bit less accuracy, or you can run it more frequently, but we think that that would be sort of overkill for most applications. Then I'm looking in the chat and see if I missed any questions there, or if it's just duplicates of what we had in the actual questions box. Would the NPM 1300 fuel gauging work with non-rechargeable batteries such as CR 2023? I corrected to 2032. No, the voltage levels are simply not in the correct range for the NPM 1300. Then there's a question: what is the resolution of current measurements performed with the NPM 1300? We provide it, or the algorithm provides it down to 0.1 volts percent. Sorry, 0.1%. Then I can't see any more unique questions. There is a comment about something not being true, and that there's more algorithms much better than the coulomb counters. Yes, then we agree. Algorithm-based fuel gauging is better than coulomb counting, and algorithm-based fuel gauging is best when you get the hardware for free in your PMIC, and you don't need an additional processor to do the processing for that algorithm. You can just use the main system processor for it. Totally agree. 3 microamp average current is the power draw of the PMIC itself. How much current is needed on system side to pull the PMIC once every second and run the calculations? No, your assumption is incorrect here. The 3 microamp average current is the power draw that is added to your application for pulling the PMIC and run the calculations once per second. The average current draw of the PMIC itself is way less than this, and it depends on the efficiency of the regulators. And and you wouldn't get away from this anyways. And if you get away from it by not using a PMIC, the internal power regulation of your SoC would typically be less efficient and actually lose you energy instead of saving you energy. So the correct answer here is 3 microamp to pull the PMIC and run the calculations. Then there's a question if I have a comparison about energy power consumption between the NPM 1300 and using a coulomb counter and using open circuit voltage. So yes, I do. So we showed in a slide in this presentation that the coulomb counter uses 50 microamps when the system is active, and the NPM 1300 uses 3 microamps. As I said, that is what it's adding to your application in terms of the software needed to run it, or the code piece needed to run it. So it's way less. Compared to open circuit voltage is free, so it doesn't add any energy, but it's also way less accurate. Then there's a question if the fuel gauge library is open source or if it's distributed as a binary, and the correct answer here is that it is distributed as a binary, but it's free to use, and also you own all the models that you are using with it, so you can tune them exactly how you like, and they are basically just CSV files that you can look into and see how they work. What is the largest capacity battery supported by Nordic chips, tools, and library support? So basically, if you can deal with having only 800 milliamps of maximum charge current, you can use as large battery as you want in terms of capacity, as long as it's on the correct voltage levels. If you're using fuel gauge and the automatic fuel gauge battery profiling application, then the charge timeout will time out after 7 hours. So 7 times 800, that's 5,600 milliamps. So that is the maximum battery size that you could profile in the app in its current state. It's also the maximum battery size that you could charge from 0 to 100 in one go without having to reset the PMIC manually. How can I automate the process of changing the temperature while the battery model is generated? Is there an API which I can use to check whether the temperature needs to be changed? As I'm aware of at the moment, I don't think there is such interface to be used. So you would have to be present manually to restart or resume the process once the temperature has been changed in your temperature chamber. But that's good feedback, and we will look into that for future developing of our fuel gauging tool. Let's see here. Is it possible to save the current fuel gauge state to restore it after reset of main system, or is it not needed? This is not needed because the fuel gauging system works in such a way that it will spend a little time, a few seconds, on recalibrating itself after a full system shutdown. So even if your system has been completely off, after a few polling of the fuel gauge algorithm, it will, or a few of the fuel gauging functions, it will regain the same accuracy and restore itself back to the correct state of charge as what the fuel gauge would estimate. And the benefit of this is that you are not accumulating errors as you would with a fuel gauge with a coulomb counter, but you're actually getting a fuel gauge that is based on the current state of the battery, even if the battery has discharged slightly while the system was off. And this relates to the next question, which is what happens to fuel gauging if I completely power down my device? And as I said, the fuel gauging stops running when you completely power down the device, but because it is made in such a way that it doesn't rely on having constant input from a coulomb counter, it will simply do a new calculation, and after running for a few seconds, it will normalize itself to the accurate estimation that it had before it was shut down. Then there's a question, would the PMIC be working with primary cell batteries? So primary cells are the name for non-rechargeable batteries. And the question here is, sort of. So there's very few primary cell batteries that operate at the voltages that are supported as a input voltage for this PMIC. But if you have such a battery, you could use the PMIC for power regulation. And if you are willing to spend a few batteries and have a battery that is on this same voltage levels, you could potentially also manage to manually create a fuel gauging model that would work with this battery, but it is not supported by the tooling because that requires charging also. Then there's a question, is there a set of existing battery profiles / characterizations available that Nordic has already done, as well as the battery used in the thingies and the decays? Yes, as you could see in the demonstration, it might not be as clear or as highlighted, but if you go into the Profiles tab of NPM Fuel Gauging app, you can see that there are multiple batteries from manufacturers Renata and also manufacturer Lipol, and that has already been both profiled by Nordic at our facilities and also validated to work well with these batteries. So there's around, I think, around 20 batteries that are available already that you can use. And if you buy a battery of the same SKU, shelf unit, and if you buy a battery of the same model, make and model, it should work great with those pre-profiled models as well. Then there's a question, is fuel gauging possible with the Thingy 53 and the NPM 1100? No, the NPM 1100 does not have any I2C communication to the host, and it doesn't have the hardware that is needed to pull out the information needed from the battery. It doesn't. So the current and temperature and voltage information is simply not available to do this with the NPM 1100. That is in the Thingy 53. Will this webinar be available to watch later? Yes, all webinars are uploaded to YouTube and webinars.nordicsemi.com after completion, along with the slides from the webinar. Then there's another question about primary cell batteries. I'm using alkaline batteries. Can I still use fuel gauging? I think that's a no. Alkaline batteries are at 1.5 volts, so they simply can't drive the PMIC. Let's see, is fuel gauge possible to do with NPM 1100 as well? No, this has already been answered. It is not possible. How does the PMIC/fuel gauge deals with partial charge discharge? This is not a problem. Due to the way it works, it will, as I said, normalize after pulling for a few seconds, it back to estimated state of charge. Is it possible to use your battery profiling application to generate a battery profile that can be implemented in a PCB assembly with NPM 1300 controlled by some part number I don't recognize? If this part number that I don't recognize uses an ARM Cortex-M4 or ARM Cortex-M33 processing core and is using or are compatible with the Zephyr RTOS, then this should be possible. Yes, I don't know this part number specifically. Then there's an interesting question if there has been a period of external drain on the battery. And with that, I am interpreting it as something that is drawing current from the battery directly without going through the PMIC. Presumably, the NPM 1300 will settle correctly, assuming the external load is removed. And I think that might be the case, yes, because it's using the voltage and temperature levels along with the current and not simply just the current. So as long as the external load is not currently loading the battery, this should equate to it settling into a more or less correct value after it is removed. Then there's a question, can the PMIC be combined with another charger, e.g. Qi wireless charger? It has not been designed for that use case, and I'm not up to date on the requirements of Qi charging chips at the moment, so I would have to pass on that question. We can look that up later. Then there's one question more about, is there any solar/photovoltaic energy harvesting IC reference examples used with the NPM 1300? As of now, we don't provide any of this, but there has been interest, so you might be able to find some use cases where this is tried, but as of now, I don't have anything to share. And then there's a question about battery aging. So this is something we are working on improving. As of today, the fuel gauge would show less than 100% at the full charge of a aged battery. And the reason for not having this implemented already is because we needed to actually age some batteries to have good testing and to figure this out. So in a update, we will update it so that even a aged battery will show 100% when it's fully charged. But as of now, it will simply show that the battery isn't fully charged, even if it is on a battery that's very aged. But this will, in most cases, take a very long time before your battery comes to that state. And it's not showing accurately at 100% or a full charge anymore. Then I think we've been through all the questions in the questions tab. Let me just check the chat. I see that there are some questions, but I think they all are duplicates from the questions tab. And there's one about if I'm talking about fuel gauging by adding hardware components, but what does Zephyr have to do with this? I think that might have been answered by the demo. So there is obviously a hardware component to this, which is a PMIC. So a PMIC is something you would typically need in your application anyway. So you're sort of getting the hardware part of this for free. And then the demo is focusing on the software component of this fuel gauging method, which is the same for any Zephyr RTOS-based application. And that is why we have named this webinar that. It is because it will be possible to implement this in software in any Zephyr RTOS application, as long as it's running on a compatible ARM Cortex M4 or M33 core. And that was what I had for you today. If you want to know more about fuel gauging, you can go to nordicsemi.com/fuel gauge. If you want to watch more webinars, you can sign up for upcoming webinars or watch webinars on demand at webinars.nordicsemi.com. And if you have more questions about fuel gauging or any questions about working with Nordic devices in general, you can go to devzone.nordicsemi.com gmail.com, and we will have one of our tech support engineers answer your question directly to you. Thanks for watching, and I will see you again next time.